Hello students, welcome to Unit 4 session. In this session, we will discuss about architecture of data acquisition system, then few case studies, and in the last we will discuss single channel data acquisition and multi-channel data acquisition system. So let's start. As we already know, data information from any phenomena, and the main process is to sampling the signals and converting them into electrical and further into digital so that it can be stored and manipulated by a computer. This is a functional block diagram of any data acquisition system. So as we discussed, it senses the physical phenomena at the primary stage. So we use transducers and sensors for this purpose. So transducers convert this signal into electrical format where we perform signal conditioning using signal conditioning circuits, and we have already studied about this thing in unit 2. So from signal conditioning circuit, the signal goes to data acquisition hardware. This involves few storage devices and further signal conditioning if it requires, but mainly it includes few interfacing hardware which is further compatible with the personal computer, that is PC, and its software. So this is the complete functional block diagram, and if we see how many functional elements are there, first one is sensors and transducer, second one is field wiring, obviously it is throughout the block diagram we can see, third one is signal conditioning element, then data acquisition hardware, and then we have software which is called data acquisition software, and finally personal computer where we display the final readings or we plot whatever physical phenomena we are acquiring. This is the PC based data acquisition systems architecture. When we involve personal computer and more IT tools, then it is always better to represent data acquisition system architecture in a similar terminology. So we'll start with the central unit, which is data logger and processor. So the data logger ultimately store all the information which is coming from the system. So system means we are doing some analysis. So this analysis could be our sensor, transducers, and finally signal conditioning system. So it sends the signal to processor. Processor further give command to data logger to store the knowledge, to store the information, either they are image files or they are text files. So they keep on recording in this storage media. At the same time, there is a data acquisition server which interacts in real time with GUI. GUI means graphical user interface. So GUI means graphical user interface. So whatever we see on the monitor screen, if it is touch screen or it is controlled by either keyboards, so whatever we are visualizing on the monitor, this is known as graphical user interface, through which any user can interact with the data acquisition system, is known as GUI. So this is the architecture. Next is one case study in which data acquisition system is used in a ECR where solar based battery charging unit has been employed. So let's see where are the basic functional elements in this system. As we are seeing that solar panels are there which are converting solar energy into electrical ones, we are sending that electrical signal to even power up the data logger, even power up the pyrometers which is used to measure the temperature, as well as we are using some part of it to feeding back to the battery so that battery can be recharged using solar energy. So there are two purposes of these solar panels. They are also providing electrical signal to the hardware, as well as they are providing additional electricity generated by the panels to the batteries for charging them. At the same time, whatever signal is being sent by the pyrometer, or if we are measuring some ECR, that is electrochemical reaction phenomena, we have even some flow meters, we have some controllers, so we can capture this information, all this information, even temperature of this solar panels, radiant energy on the solar panel from the sun. So all this information can be used to store through this data acquisition hardware. So this is a complete system where we can employ and we can understand how physical phenomena interacts with signal conditioning circuits, few transducers like pyrometers, and then devices like data logger and hardwares, ultimately providing the information at personal computer for real-time display as well as for storage of the data. Another very good example is in hospitals or in biomedical engineering. We are controlling and managing MRI scanners, because in MRI machines there are a lot of pneumatics, mechanical and electrical equipments to be controlled. Mechanical, like positioning of this bed. You know, when a patient is lying on this bed goes inwards so that the head of the patient can be within the scanner. Okay, and after the scanning this bed comes out. So it means there is some mechanical movement being controlled by a robotic device, as well as there is a scanner in this particular block. So we are controlling many equipments, as well as we are acquiring the signal being scanned by this scanner. So let's see how it is happening here. If we can understand the terminology being used for the color coding, this dot or dash line is a digital signal. Digital signal is being sent by the MRI scanner to the data acquisition port. So it means MRI scanner itself is a digital system which scans the slices of human brain, converting them into a digital format so that a computer can directly interface with this particular data. So as you know, JPG format or DICOM format, they all are in digital format. So MRI scanner is connected with data acquisition port through digital data signal. Then we have this red color code for fiber optical cable, so that we can provide the signal as well as we can get feedback from this robotic device. Why do we need feedback? So that we should come to know the exact position of this bed where the patient is lying, whether it is inward and how much percentage of this bed is inside the scanner. So one is controlling signal like proportional valve, which is a pneumatic pipe. Pneumatic means which works on air pressure, because we need to move the mechanical parts. So it may be either electrical signal or pneumatic signal which are used to move the mechanical systems. So in this case we are using pneumatic, and that is why air supply is being used to fed into it, so that air pressure ultimately drives this driving system, due to which it moves to and fro. And to get the right position we have a feedback signal which is being provided to the again data acquisition system, which calculates its current position. Then there is one emergency position switch also, and the whole comes under the control box. So here we can say again the DAC, that is data acquisition unit, is central part of this complete system, and this is the DAC only which interacts with the PC. So whatever information is coming from every corner, every bits and parts from the system, it comes through the data acquisition system, where ultimately the information is sent to personal computer, and after that decision again it is given back to data acquisition system, from where again some decision has been implemented back to the MRI scanner. Now let's discuss about few important parameters of data acquisition system. It is very similar to other instrumentation systems, so that's why we have similar kind of terminology here as we studied in earlier subjects like accuracy, precision, resolution. So, similar kind of terminology is here for data acquisition system. So, first one is accuracy, noise, then we have settling time, acquisition time and resolution. So, let us see one by one of them. Accuracy is very similar to what we have studied in measurement system, that is, it is the degree of closeness to the measurement value, means whatever the known value is with us, the closeness of that measurement value with the true value is known as accuracy. And precision means reproducibility or repeatability of the measurements. It means if the measurement system giving you the readings same for the same input, it means it has the reproducibility to reproduce the same output for the given set of inputs. Then we have noise, and it is again similar, like where there is interference, where there is a common mode noise, they all comes under into the noise, that is an unwanted signal is known as noise. And usually in this case in data acquisition system, because we have power signal also, so most of the time we are handling 50 hertz power frequency as a noise. Although we have many filters in data acquisition system hardware, but still we have to take care about how much noise carrying capacity is there within the system. Next parameter is settling time. As we know, when the data acquisition system start acquiring the data, there is some transition, and after that transition the system output gets settled down. So, whenever that output gets settled down within the 10 plus minus 10% or plus minus 5%, there are different ranges for the definition, or plus minus 2%, but usually we take plus minus 5% of the final value. So, when the final output settle down within the plus minus 5% of final value, we say this is the settling time. So, in this diagram this is TS. Now comes to one new term, that is acquisition time. We know that in most of the data acquisition system, because they are built around digital systems, we have to have A to D, that is analog to digital converter. So, there is a time when analog signal is being sampled by the A to D. Once it is sampled to a particular level, let us say at this level the signal was sampled, so it will be hold for some time at this value only, and during that time this analog signal is converted into digital 1 0 0 0 1, something like this. So, the time within which any analog quantity is being converted into digital 1 for the next transmission is known as acquisition time. Okay, so it means the complete acquisition time definitely depends upon A to D acquisition time as well as other time delays within the signal, but minimum acquisition time will be equal to the conversion time of A to D for analog to digital conversion. Even it may be more than that due to other delays or propagation delays within the IC. However, it may be in milliseconds or even microseconds, but there is some acquisition time for which we have to keep in our mind regarding programming and decision making. So, coming to the last point or last parameter, that is resolution. So, it is again similar to our system design, that resolution is very important. Either if I try to compare a 16-bit versus 3-bit resolution of any sine wave, if I try to convert any sine wave into digital one, if I have only 3-bit conversion, the signal will be very much of square or a rectangular one, because we have very less number of bits to convert this signal. But as we keep on increasing the number of bits, the levels will start increasing. Let us see how it happens. Suppose we are converting 5 volt or a 0 to 5 volt signal into its corresponding digital levels. If we have 3 bit means 2 raised to power 3, so it means we have only 8 levels. So it means we have to divide 0 to 5 volt signal into equal 8 parts, something like 1, 2, 3, 4, 5, 6, 7. Now there are 8 equal parts, similar, almost equal parts. So the resolution will be 5 volt divided by 8. Okay, so it will be around 6 point something. Okay, 6.4 or something like this. So this is the minimum, sorry, 0.64 volt. That is the minimum value that we can measure through 3 bit. If I increase the resolution to 10 bit, let's say this is now, instead of 3 bit we have 10 bit resolution. So we have 2 raised to power 10, which is equal to 1024. If on a generalized scale, if I take it as 1000, so you can imagine now 5 volt is being converted into 1000 level, so which is almost 0.005 volt. So see the difference. So as we increase the resolution, that is why we can measure the input signal, or we can quantize the analog signal into very highly resolving signal. So that is the advantage of high resolution data acquisition systems. Now let's discuss something about MyDAC. MyDAC is hardware which is available in our lab. We will try to perform some experiments or do some demonstration. This hardware is made by National Instruments, popularly known as NI. I hope you people are aware of LabVIEW, which is a software, very popular software being used in the industry for data acquisition and controlling many instruments. So this MyDAC is compatible with the LabVIEW, as well as it can directly interact with many hardware components, and it can handle 0 to 5 volt signal, 0 to 12 volt signal, even more than 12 up to 24 volt we can handle. Let's see more features of this MyDAC. So MyDAC is something like very portable data acquisition system. So the first feature I should mention is it is very small and portable data acquisition board, which is useful in constructing a data acquisition system, because for complete data acquisition system we need some sensors, but rest of the part, starting from signal conditioning, DAC hardware, everything is available in this unit. You have to need few sensors where you can have, because it can directly be plugged into, see, analog input, digital input, there is power supply available, okay, and through computer we can connect it through USB port. So we can even power through the USB if we have to have only 5 volt, but if you want to give more voltage, higher voltage to this, you need to have provide that higher voltage through these power supply pins, that is plus minus 15 volts. So inside operational amplifiers will work only if you can provide up to this much voltage from outside. So we have to provide outside voltage like plus minus 15. So internal circuitry will get automatically energized, and it can handle 16 bit sampling rate, that is sampling rate is 20 kilo samples per second, that is the sampling rate of this particular DAC card, okay, and its conversion is 16 bit conversion, and it can handle up to plus minus 10 volt, that is peak to peak signal it can acquire is plus minus 10 volt. It can also acquire sound signal, that is there is a sound 3.5 mm jack which can directly be plugged into any sound system, so it can acquire sound signal also, it can sample sound signal, it can convert that sound signal into digital one. Some of the students have used this device to capture heartbeat that is being captured by some microphone, and they plugged in microphone with 3.5 jack, and they plugged in that jack here, and rest of the work done by all this hardware, because ultimately with the computer it was connected through USB, and on the PC we have LabVIEW software with us, which can easily integrate with this hardware. So LabVIEW work as a driver as well as GUI. So we can perform many functions, like we can convert it into digital multimeter. We can use this board as oscilloscope, function generator, that is we can generate few functions using LabVIEW. Through LabVIEW they will come to this board, and through board we can generate those functions either analog output or through digital output pins. So you can imagine power of this particular board. It is very useful in lab, in prototyping, in designing systems. So in your capstone project you can use this board. It is very useful. So it is simply plug and play with the LabVIEW. So here is the slide where we have many functionalities. Using the same card we can generate functions. We can use it as a digital reader, even Bode plot analyzer. So many functions can be designed within the LabVIEW using the same hardware, that is MyDAC. So what is MyDAC? MyDAC is a portable data acquisition hardware which is very useful, and it can be easily integrated with LabVIEW. There is very small application, that is you can also have a motor control without any LabVIEW. You can have motor control and you can directly provide analog signal, and using this you can directly control the motor. So it means by connecting a potentiometer also, if I have a potentiometer I can connect that input here, and using that change in voltage we can control the speed of motor. You can also connect this through USB to any PC, and using LabVIEW we can also control speed and direction of this motor. Now let's come to the final slides. This is about types of data acquisition, that is single channel and multi-channel. The first type is single channel data acquisition system. Single channel consists of only one channel at a time using an analog to digital converter. It means whenever we are having a single channel signal conditioner followed by an A to D converter, okay, that is known as single channel DAC. Okay, it means we have a single channel A to D which is converting different signals but one at a time. Whichever signal is being selected, that can be converted into digital and finally sent to the next stage. So it means that is single channel. We can handle only one channel at that time, but we can repeat that performance for other samples, but only one signal can be handled at once. However, in multi-channel DAC we can handle multiple signals parallelly, because for that we have multiple A to Ds and other filters all embedded into this signal conditioner. So whenever we have multiple number of signal conditioner, and that too of different ranges, as we have seen in MyDAC, some of the A to Ds are, let's say, 8-bit, some of them are 10-bit, some signal conditioning is working from 0 to 5 volt, some is working at let's say 0 to 12 volt. So there are different signal conditioning. One is giving you TTL output, one is giving us RS232, and maybe one is giving us 5 rather than 5 volt, it is giving some 12 volt, and this is giving analog output. So there may be different types of signal conditioner circuits which are working parallelly, So it means we can handle a number of input signals in parallel. That kind of data acquisition is known as multi-channel data acquisition system. Like in this diagram, it is more clear, that is, the main part in this case is DAC blocks, which are equal in numbers, the numbers we are having different sensors. So we have analog to digital front. So each analog signal is sent to individual DAC block. So there are number of DAC blocks, that is data acquisition or signal conditioning devices. Each of the block contains A to D, that is analog to digital converter. Then we have some control signals, some memories, some FPGA, other things, and finally we have a DAC switch, which ultimately tell the PC, or PC gives the signal to DAC that at which time which signal is to be sent to the PC. So every DAC block is ready to send the signal, but host PC provides the information to DAC, and DAC switch further decide which information needs to be sent to PC. So this is all about multi-channel DAC. I hope you enjoyed this video session, and thanks for watching this video.